So hello nerds, this is Suman and in this video I'm going to talk about nothing. So basically in my last I think fourth or fifth video I had discussed about the concept of Heisenberg uncertainty principle and its extension. Whether I have to call it an extension or not, I really don't know, and I really don't know whether it is physically consistent or not. So I haven't used the momentum operators or something in terms of quantum mechanics. The idea is purely based on algebraic expression. So yeah, in that video, the video quality is very much low. The video quality is very much low, and you might haven't understand the approximation I have done, and I really didn't talk much about the concepts. So I'm making this video again, and and you can actually watch it also. So it is purely based on the Heisenberg uncertainty principle and looking it through a various perspective, right? So looking at Heisenberg uncertainty principle in various perspective might enables us to various interesting things. If you had seen that video, I had derived it in based on kinetic energy based condition, the relativistic energy based condition, and how I had made the general relativistic case to the normal classical case, the special case. So one can actually do the same thing from the normal case and prove it. So I'm making this video just to provide a better quality video. So in that video the video quality is very much low, I guess, and I'm still in a learning phase where I'm learning the new things. So I have to do it, and whether this video is going to be a good quality or not, I really don't know, but I try to make it as far as possible. So up to here, let us dive into the whiteboard and let's see what is the beautiful result we will get by doing the approximation, by using the Lorentz factor and various things, and just making the special case how the Compton's wavelength is associated with the particles that has mass, and let's do other things also. So let us dive into the whiteboard. So nerds, let's derive the relativistic condition as well as the kinetic energy based condition. So let's do it. So I'm actually feeling bored because I had done it more than 100 or even more than 100 times. The same thing. Okay. So I know that from Heisenberg uncertainty principle. So actually from Heisenberg uncertainty principle, what we can write is the position uncertainty. So position uncertainty is written as like that. And the momentum uncertainty of a particle is greater or equal h over 4 pi. Yes, it is h over 4 pi. Okay. So now you can reduce this equation into product of position uncertainty and momentum uncertainty is h cut over 2. So h cut is nothing but your h over 2 pi. So this is called the reduced Planck's constant. So basically this is our reduced Planck's constant. Let's consider it as equation number. So if you have already seen the previous video, you do not have to watch it again and again and again because it was in a very low quality. I'm supposing that it would be in very good quality. So I do not have a perfect editor or something like that. And we know that when the particle is in motion, there will be some associated wavelength within the particle, and it is given by the de Broglie wavelength, right? So we can state from de Broglie wavelength. So if you don't know if the particle is in motion, it has associated wavelength with it, and it was confirmed by the famous experiment done by Davison and Germer. So the momentum can be written as H is our old-fashioned, very famous Planck's constant over the wavelength associated with particle. Okay, that is nothing very mysterious. So I am writing momentum is h over 2 pi into 2 pi over lambda. H over 2 pi and 2 pi over lambda. So I get momentum is, this is nothing but the reduced Planck's constant. It's sometimes it's called H cot or Dirac bar or something they call it. And 2 pi over lambda is nothing but the wave number associated with that particle, right? So this would be my equation number second, right? Right. So in terms of momentum uncertainty, we can write our equation, the equation number one, in terms of the wave number uncertainty. So how I am going to write it? So I am basically using equation 2 in 1. So when we put equation 2 in 1, we get delta x into. So in terms of momentum uncertainty, we can write h cut delta k is greater or equal h cut over 2. So the position wave number uncertainty is greater or equal to 1 by 2. So from here you can actually see that the uncertainties are always positive. So it has to be positive quantity, right? There is no chance of getting negative uncertainty. So if there is a negative uncertainty, the terms and terminology might look very much different. So you are trying to measure a particle within a positive x-axis, and then might your wavelength uncertainty will be in negative x-axis. So this might not be the possible. I guess. So this would be my equation number third. So as earlier I had write the momentum uncertainty in terms of wave number uncertainty. I want to write the uncertainty in wave number in terms of wavelength. So if I had to do that, I know that I can write delta k is dk over d lambda into delta lambda, right? So delta k is d over d lambda, and this is 2 pi over lambda and delta lambda. So if we were going to take the magnitude, but the students already understand that the negative sign will come and the uncertainty is always positive, so we have to use the magnitude, and we will get 2 pi over lambda square delta lambda. So this also makes sense, I think. These things also make sense, right? So this would be my equation number 4. So I am using 4th in equation number 3rd. 4th in equation number 3rd. So what would I get? So I will get delta x into 2 pi over lambda square. Delta lambda is greater or equal 1 by 2. So I get a new relation that the position wavelength uncertainty of a particle is always greater or equal its wavelength squared over 4 pi. Wavelength is squared over 4 pi. So this would be my equation number 5th. So this would be my equation number 5th. So this would be my equation number 5th. So okay, you can actually see from there that the product of uncertainty increases as the wavelength goes on increasing. So if you plot the graph, putting the uncertainty in position and wavelength and taking your wavelength variation in x-axis, you will end up getting a parabola. So I think the uncertainty is actually never be zero because the wavelength cannot be zero. So there must be the graph must be always start from this. So the minimum possible value of uncertainty is here, and this would be lambda square upon 4 pi. So this range, so basically this range would be your lambda square upon 4 pi, and the uncertainty can be greater than this value. So this can be and the greater than this value can lie here, 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 and it goes and increases. So the graph actually predicts that. So why I'm not starting from 0 point? Because the minimum possible uncertainty is this much, lambda square upon 4 pi, if we neglect the inequality sign. And if you put the inequality sign, the uncertainty goes on increasing. So starting from 0, it doesn't make sense, because if you start from this term as 0, your wavelength must have to be 0, but particle do not have wavelength 0. So you can actually say that this thing starts from 0 when the particle would be at rest. So if your particle would be at rest, the momentum of particle is 0. The momentum of particle is 0, and the wavelength of particle tends to infinite. Wavelength of particle tends to infinite. So starting from 0 doesn't make sense, I think. Okay. So up to here we have got an interesting relationship, and this is the good result, I guess. So delta x into delta lambda is greater or equal lambda square upon 4 pi. So I am going to replace it, and I am going to manipulate the terms here. I am multiplying and dividing by p square, the momentum squared of particle. So what would I get? Delta x into delta lambda is greater or equal. So if you had already seen that the the product of wavelength and momentum is nothing but the Planck's constant. This immediately follows the de Broglie wavelength. So this is h square over 4 pi p square. H square over 4 pi p square. So let us apply this condition to the relativistic effects. So energy, we know the energy momentum relation. So the energy momentum relation. So we are doing from the energy momentum relation that your energy squared is m0 squared c power 4 plus p squared c squared. So this is the energy momentum relation. This is the energy momentum relation. So I want to replace in terms of momentum, so I am going to put my m0 squared c squared in the side of e squared, and I can, let's do it in for the next step. So p square can be written as e square minus m0 square c power 4 divided by c square. So if you had seen here, you can actually see I am just doing e squared into m0 squared c power 4 by m0 squared c power 4, and it makes sense, minus m0 squared c power 4 divided by c squared. So it makes sense because I want to write in terms of the Lorentz factor, so I am doing this thing. So the momentum square is nothing but, if I take this common, m0 square c power 4 by c power 4 here, and I will end up getting e squared over m0 squared c power 4 minus 1, right? Here is c squared, and the square and the power 4 will cancel. It doesn't cancel all those things. Right. So we can write the relativistic energy. So you can write the relativistic energy E is gamma m0 c squared. So let me put in a frame that the m0 is the rest mass energy of particle. So the energy increases gamma times the rest mass energy. Okay. So if you take your E and divide it with m0 c squared, you will end up getting gamma. So if you square both sides, you will have to raise speed of light as power 4, and these terms look might familiar to you in here also. So you can write your momentum is m naught square c square, right? M naught square c squared gamma squared minus 1, right? M naught squared c squared gamma squared minus 1. I haven't done anything wrong here, because if you divide this side with m naught c square and square it, you will end up getting this relation. So in terms of momentum squared, we can write in terms of Lorentz factor. So the equation here, this equation, so this equation would becomes delta x into delta lambda is greater or equal h squared over 4 pi, and in terms of p square you can write m naught square c squared gamma squared minus 1. M naught squared c squared gamma squared minus 1. The gamma is nothing but gamma is 1 over under root 1 minus v squared over c squared, right? So if you know the concept of Compton wavelength, the Compton wavelength is written as h over m naught c. So here we have h square m naught square c square. So if you square here, you have to square all of them. So you will end up getting delta x into delta lambda is greater or equal lambda c squared, the Compton's wavelength squared, over 4 pi gamma squared minus 1. Gamma squared minus 1. And now if you are going to plot a graph, with delta x into delta lambda, I'm just putting the rough graph. I haven't done any experiment in this mathematics, so I let it do it for the experimental physicist. So with increasing gamma, look up to here. With increasing gamma factor here, your uncertainty, product of uncertainty will goes on decreasing. So it will goes on decreasing like this. It will goes on decreasing like this, right? So this is relativistic effect on uncertainty. This is the relativistic effects in uncertainty, right? Okay, up to here it makes sense. So you can see very much interesting thing. So if you allow me, for an instance, and let me do this thing, if you allow me to neglect this 4 pi term for an instant, let's just see what we'll get. So if you let me neglect this term, and let us approximate our gamma squared minus 1 is approximately equal 1, and we are neglecting 4 pi for an instance. Neglecting 4 pi for an instance, we will end up getting the position wavelength uncertainty is greater or equal Compton wavelength square, approximate value. So this would be approximate value. So basically you can say that you cannot have uncertainty less than Compton's wavelength squared. So your uncertainty will always be greater or approximately equal to the Compton's wavelength, right? Or it has to be nearly approximate up to the Compton's wavelength, or it could be greater than this if we apply an equality sign here. So this, I think, is going to make sense for you also. So the Compton's, this is the fundamental property. So this is very much fundamental property of, I think this is the fundamental property. Not much fundamental, but it is actually. You can see in terms of your position wavelength uncertainty is the Compton's wavelength variation. So this is our relativistic case. So can we reduce this equation into non-relativistic case? So for this we have the approximate gamma, right? For this we have to approximate gamma. Okay, let's do the approximation. So let me write non-relative non-relativistic case. So for non-relativistic case, we have to replace gamma is equal, we have to reduce the gamma factor. So we know that the gamma is nothing but 1 over under root 1 minus v squared over c squared, right? So if we square both sides, you will get gamma squared is 1 over 1 minus v squared over c squared. And if you take this above, you will end up getting 1 minus v squared over c squared raised to the power negative 1. So you can actually approximate like this: 1 minus x raised to power negative 1 is 1 plus x squared plus x cubed plus so on and on. So you can actually approximate this. So your gamma square is going to be 1 plus, in terms of x we have v squared over c squared. So v squared over c squared plus v4 over c4 plus so on and on. So we are dealing with a non-relativistic effect. So we are dealing with a very much low speed. We can actually neglect these higher terms and we can actually take this gamma square is approximately for us as 1 plus v squared over c squared. So you can write it as gamma squared minus 1 is approximately equals to v square over c square. So the gamma squared is approximately equal to v squared over c squared. Right? Okay. Okay. And now I'm going to replace it up to here. Let's do it here. So let's do from here to there. So in terms of position wavelength uncertainty, I have lambda c. Let me write this in terms of momentum and in terms of in its actual form, h square over 4 pi m naught square c square. And in terms of gamma squared minus 1, we can approximate this value up to v squared over c square. So v squared over c squared. So c squared we're going to cancel out and you will end up getting delta x into delta lambda is greater or equal h square over 4 pi m naught square v square. So this is the normal speed scenario. In terms of normal speed, you will end up getting this thing. So this is for the normal speeds, not for the speed is comparable to light. So if you are going to plot the graph again further, here you can see h is constant, 4 pi is constant, m naught is the rest mass of particle. So rest mass of particle. This don't you think that it applies for photon? It doesn't apply for photon. It applies for the such particles which are heavier than photons, because the photon do not have rest mass. So does electron do. So it is going to, if this works, it is going to apply for the electron, proton, neutron and other particles with mass, with rest mass. So if we change the velocity of particle here, because the particle can exhibit any kind of velocity, it would be 10 meter per second, 20 meter per second, 100, 50, 200, 2000 meter per second. You can depend on your choice. You can actually accelerate particles using potential. So in terms of this x-axis, I am writing v, and in terms of y-axis, I am writing my uncertainty in position and wavelength for normal speed. So there will be a speed of particle, you are doing experiment, and the corresponding uncertainty. So the uncertainty actually decreases, and it will decrease more rapidly because it decays. I don't have to say whether I have to say it decays or not. It will actually reduces v squared time. So it will going to give us graph like very steep graph. It is going to give us graph like this. So this would be my uncertainty relation. So this is for non-relativistic non-relativistic effects. This is for non-relativistic effects, right? So, one can actually derive the same idea from the kinetic energy based condition. Let me do that for you. So I hope up to here you had understand something interesting. I might be wrong because I hadn't used any kind of operators for the quantum mechanics. Okay, let us derive from the kinetic energy based idea. So up to some point we have derived uncertainty position and wavelength is greater or equal h square over 4 pi p squared. If you had remember, so you do not have to remember all this formula because it doesn't show in our textbook. You have, if you had seen, there will be only form of Heisenberg uncertainty principle, that is delta x into delta p is greater or equal h over 4 pi. Okay, so if a particle is actually moving with velocity v, and from Einstein, according to Einstein, the energy of particle is going to increase, so does mass. So the total energy of particle can be written as m naught c square, the rest mass energy plus kinetic energy, right? So basically this is the rest mass energy and the kinetic energy. So you have rest mass energy and you have some additional kinetic energy due to your velocity, then the total energy becomes m naught c square plus kinetic energy. So you can write your energy term as gamma m naught c square. Your energy will increase gamma times m naught c square minus m naught c square is going to be your kinetic energy. So you know that the kinetic energy nothing that is 1/2 mv squared. So in terms of, you can write is m square v square over m. So you will end up getting 1/2 p square by m. So you can actually take common 1 minus gamma and you will end up getting m naught c squared gamma minus 1 is equal to p squared over 2 m naught. So this would be my rest mass energy because we haven't applied for the relativistic condition. So if I go here, I will get 2 m naught square c square gamma minus 1 is my p square. So p square will be 2 m naught square c squared gamma minus 1. Right. So in terms of momentum squared, I can write in terms of Lorentz factor. So delta x into delta lambda is greater or equal h square over 4 pi, and in terms of p square I can write 4. If you look, see here 2 and here 4, and it will end up getting us 8 pi m naught square c squared gamma minus 1. It is not r, it is actually gamma. It is actually gamma. Right? Okay. So again, let us approximate our value. So the gamma term is nothing but 1 over under root 1 minus v squared over c squared. So because the earlier, if the non-relativistic case in the earlier section we have found must have to be the same as the normal kinetic energy based case, because it is also the non-relativistic idea. So I get gamma, and if you take this whole thing up, you will end up getting v squared over c squared raised to the power negative 1 over 2. Right, and if you do the binomial expansion of this, you will end up getting gamma is 1 plus 1 by 2 v squared over c squared plus, I think there will be 1 by 8 and there will be higher term, and we can actually neglect that. So I am approximating gamma. So gamma is approximately equal to, for our non-relativistic case, gamma is approximately equals to 1 plus 1/2 v squared over c squared. So gamma minus 1 is approximately equal to 1 by 2 v squared over c squared. So you can substitute in here, and you will end up getting delta x into delta lambda is greater or equal h squared upon 8 pi m naught squared c squared. In terms of gamma minus 1, you can write as 1 over 2 v squared over c squared, and you can cancel out each other, and this would be 4, and this would be delta x into delta lambda is greater or equal h square upon 4 pi m naught square v square. And this is the same classical idea that we had already derived from our relativistic effects. So I think the video quality is very much good now, right? So up to here, so this is again the same non-relativistic idea, So this is our relativistic idea. Delta x into delta lambda is greater or equal lambda c squared upon 4 pi gamma squared minus 1. I think my mind has already memorized all this formula because I had done it for more than 100 times. Even more than 100 times. So this would be the completely relativistic effect, and this would be the non-relativistic case. This would be relativistic. You can see that there is a gamma squared for the completely relativistic, and there will be gamma for, I think, non-relativistic. So it might be the moderate relativistic. I don't know so much about all this, but I know about the graphs and whatever thing. So up to there, bye bye, and just make sure to share these things with your teacher and let you blow your teacher mind.